Okay, so now what we're going to do is take a look at probably one of the central aspects of when we discuss gases, and that is this whole idea of the gas laws. And just like most other laws, gas laws are just simply summaries of observable behavior, and those summaries are usually in the form of equations that are going to describe how gases behave. We can also use them to predict different parameters, different characteristics of the gas. So equations that describe gas behavior. And when it comes to these gas laws, again, the key thing here now is that there are equations and they're mathematical equations that we're going to be using, which means that, yes, we're going to be doing a bunch of calculations. And what is going to be very important when we start using the gas laws is your skills in manipulating equations. So specifically now we're talking about algebra, algebraic manipulations of equations. Okay, and as we'll see as we go through some examples, all of the gas law problems you'll see really just boil down to mathematics, and specifically manipulating equations. So algebraic manipulations of equations is what we're looking at. So these gas laws then are going to relate four parameters for our gases, several of which we've seen before. So let's list them. So the four parameters that we're going to relate to each other are pressure. So we talked about pressure in some detail already. Pressure is often abbreviated big P. And remember, that's the force per unit area. And whenever gas particles bombard the walls of a container, they will exert pressure. Gases also occupy a volume. They expand to fill the volume of the container. So volume we abbreviate as uppercase V. We also are going to look at the temperature that the gas is being held at. Temperature is abbreviated big T. And the key thing about temperature and gases is that the temperature needs to be in Kelvin, the thermodynamic temperature. Okay, and that's probably the easiest thing to do, but it's also the easiest thing to forget when we start doing our calculations. So it's really important that you pay attention to that. Remember, when we go from Celsius to Kelvin, right, the Kelvin temperature is simply the degrees Celsius plus 273. So again, it's a simple conversion, but it's so simple that we often forget to do it. And the last thing is the amount. How much of the gas do we have? And this is typically abbreviated in N, and this here is the number of moles, usually. But as we know already, we can be given the amount in any other unit, grams, for instance. We should then be able to convert it to moles. So these are going to be the four things, P, V, N, and T, that we're going to relate to each other via the use of these gas laws. Okay, so let's take a look at the first gas law. And all of these gas laws are named after people, usually. The scientists that either observed or developed these laws. The first one is Boyle's law, named after Boyle. And what this says is that the pressure, so the Boyle's law relates pressure, P, and volume, V. So whenever we are trying to relate these different parameters, usually we relate a couple of them to each other. The other ones that are not involved, what we say is that we're going to keep the other parameters constant. In other words, those other things are not changing. So we can ignore them for all intents and purposes because nothing is changing in those. They're the same. What we can do is we can change either the pressure or the volume, and then we can measure, we can observe the change that that happens to the other thing. So Boyle's law says that the pressure, the P, of a fixed amount, so the amount N is constant, of a gas at constant temperature, so T, so fixed amount means that N is constant. Constant temperature obviously means T is constant, so we can ignore those. Those are not changing. We're just looking at P and now V. So the pressure of a fixed amount of gas at a constant temperature is inversely proportional to the volume of the gas. All right, so what we say is V, the volume, is proportional to 1 over pressure. Another way we can do that, remember, this is our proportionality symbol. Or proportionality sign. When we replace that with an equality sign, so if we say now V is equal to 1 over P, what we normally need to introduce is we need to introduce some sort of a constant here. That's the proportionality constant. We'll just call that lowercase k for right now. So if we rearrange our equation, what we end up with is P times V is equal to K. Right, and K here is the proportionality constant. And really that constant ends up being just a product of the other two things that are constant, the N and the T. So what this means then, if I multiply the pressure and the volume, right, I always get a number K that doesn't change, right? That's what constant means. This number doesn't change. Now, that's the way that we express that relationship mathematically. How it is more useful to us is if we relate initial conditions, so starting conditions. So initial are starting conditions to the final conditions or ending conditions. And this is where all of these gas laws are going to be way more useful to us. We can represent this PV equals a constant via this equation here. So we can say P1 times V1. So the subscript ones, we've seen those before, for example, in the dilution equation in the previous sections. So the ones here represent initially or initial conditions. If I multiply P times V, well, according to this equation up here, I should get a value, K. And that should be the same value if I multiply the pressure and the volume at the end, our final conditions. I should also get K, right? So K is equal to K, obviously, and K is equal to PV. So we can make this equation here valid, right? So we are relating initial to final conditions. We use the subscript 1s for initial, the subscripts 2 for final. So P1 V1 equal P2 V2. That is the mathematical way to express Boyle's law, the pressure volume or the PV relationship. Now, what this means is, and we've seen there's an inverse relationship between these two. So between pressure and volume. So what this means is that as the pressure increases, the opposite happens to the volume. The inverse happens to the volume. That means the volume would have to decrease. And then conversely, as the pressure decreases, the volume then is going to have to increase as a result of this inverse relationship between those two parameters for our gases. Right? We can actually plot that, actually derive or get some experimental evidence to support this law. So if we have a volume of a gas and we increase the pressure, right, what we'll actually see is that the volume decreases as a result of increasing pressure. So it becomes a nice little curve. If we plot instead volume versus 1 over the pressure, we actually see that we have a straight line. All right, so either way, there is that inverse relationship that we can plot graphically. We can, do all sorts of experiments to support this Boyle's law. So let's take a look at an example. And this particular example that we'll start with is the way that you want to approach all of the gas law problems that we're going to see from this point onwards. You are not going to be told, this is your P1, this is your P2, this is your V1, this is your V2. No, these are all word problems typically that you're going to be posed with. Okay, and what you need to do, and this is an important skill, is you need to extract the relevant information. In other words, list what you're given, and then based on what you're given, what you need to find, we can then deduce or decide, figure out which law to use. Okay, so let's take a look at this first example. It says calculate the volume. So right away, we need to find V, whether that's V1 or V2, we don't know right now, of a sample of gas at 5.7 atm. Okay, so atm is atmospheres, that's a unit of pressure. So this is P equals 5.75 atm. If it occupies 5.14 liters at 2.49 atm. So this is another volume, and this is another pressure, right? And those are related to each other. So those are both either initial or final. Let's just assume that they are initial conditions. So that's my V1 is equal to 5.14 liters. And then that would be at my initial pressure, P1, which would be at 2.49 atmospheres, which then suggests, if I go back to what I listed before, the 5.75, that's going to be my P2, and that would then mean the volume that I need to calculate is my V2. So I'm relating pressure and volume, obviously, in this problem. We're assuming constant temperature, so based on that, we're going to use Boyle's law, P1 V1 equals P2 V2. We need to solve this for V2, our unknown. Okay, and this is where your skills of algebra are going to be very important. We need to solve this, isolate V2 on one side, remove everything else to the other. So we can divide both of these sides by P2. So the P2 cancels out here. So what we end up with then is P1 V1 over P2 is equal to V2, right? So we've isolated our unknown on one side, and then we're just going to substitute our values into this equation. Okay, so we have our P1, which was 2.49, and keep track of your units because that will tell you whether you've done the manipulation correctly. V1 is 5.14 liters. Okay, and that's over P2. P2 is 5.75 atmospheres. So now I can see my atmospheres cancel. The only unit I'm left with here is liters. That makes sense. I'm trying to find volume. So that tells me I did the algebra correctly. And then if I plug that into your calculator, well, you plug it into your calculator, you get 2.26 liters as your final volume or as your answer in this question. And then the final thing you need to do is you need to ask yourself, does this number make sense? Well, what did we do to the pressure? Well, we went from our initial pressure of 2.49, we increased the pressure, so pressure went up from 2.49 to 5.75. We would expect then, based on the inverse relationship, for the volume to decrease. And the volume started off as 5.14, and it went down to 2.26. So yes, that final answer does make sense. So when you, not just with this problem, with all the other ones that we'll see, again, you have to extract the relevant information from the question, list it ideally, and that will help you figure out which relationship we're going to use. We're going to select the correct gas law, solve for the one unknown, and then substitute your values in, keeping track of the units, and then solve for it.